Okay friends, the characteristic impedance Z0 is thus Z0 is equal to square root of Zy. Square root of Z by Y. So Z is written as R plus J omega L by G plus J omega C. Square root of R plus J omega L by G plus J omega C. If the resistive terms of if the resistive terms are negligible, the equation for Z naught collapses to the result we have derived earlier, that Z naught is equal to square root of L by C. Because the impedance approaches the square root of L by C at sufficiently high frequency, independent of R and G. So independent of R and G, so it is sometimes known as the transient or pulse impedance. Okay, transient or pulse impedance. Next, the propagation constant. In addition to the characteristic impedance, one other important descriptive parameter is the propagation constant, usually denoted by gamma. The characteristic impedance tells us the ratio of voltage to current at any point on an infinitely long line. But the propagation constant enables us to say something about the ratio of voltages between any 2 points on such a line. That is, gamma quantifies the line's attenuation property. Now we are considering the voltages at the two ports of a given subsection. The ratio of these voltages is readily computed from the ordinary voltage divider relationship. Ordinary voltage relationship. So A to B LdZ into RdZ ZdZ, these are two equal to ZdZ, and propagation constant 1 by YdZ. So CdZ, GdZ, Z naught. Vn plus 1 is equal to V of n into, so Z naught, Vn is equal Vn into Z naught is parallel to 1 by Y dz, and both zdz plus z naught is parallel to z naught zdz plus e2 parallel. So Vn plus 1 by Vn is equal to Z naught parallel to 1 by Y dz by Z dz plus Z naught is parallel to 1 by Y of dz. So here we can be written as Z naught by Z naught into Z by dz square plus Z naught plus Z dz. Because we will use this expression in the limit of every small dz, we may discard the term proportionally to dz square and again use the binomial expansion of 1 by 1 plus x to preserve only the first order dependence on dz. That is, Vn plus 1 by Vn is approximately equal to z naught by z naught plus z dz is equal to 1 by 1 plus z by z naught into dz. Bn plus 1 by Bn is approximately equal to 1 minus z by z naught into dz is equal to 1 minus square root of zy into dz. So let us rewrite the previous equation as a difference equation. Vn plus 1 is equal to Vn into 1 minus square root of zy into dz. So v plus 1 minus vn by dz is equal to minus square root of zy. In the limit of 0 dz, the difference equation becomes a differential equation. The solution to this first order differential equation should be familiar, that v of z is equal to V of z is equal to V naught into e power minus z into yz. V naught is initial voltage at z is equal to 0. Z represents the direction, that is the voltage at any position z is simply the voltage V naught times an exponential factor. The exponential is conventionally written as minus gamma z, so that it lost gamma is equal to square root of zy is equal to or square root of r plus j omega l into g plus j omega c. To develop better feel for the significance of propagation constant, first note that the gamma will be complex in general. Hence, we may express gamma explicitly as the sum of real and imaginary terms, that gamma is equal to square root of r plus j omega l into g plus j omega c is equal to alpha plus j beta. Here, alpha is attenuation constant and beta is phase constant. V of z is equal to v naught into e power minus gamma z. So is equal to V naught into e power minus alpha j plus V of z is equal, alpha is attenuation constant and beta is phase constant. So V of z is equal to V naught into e power minus gamma z is equal to V naught into e power minus alpha plus j beta. That is equal to V naught into e power minus alpha z into e power minus j beta z. The first exponential term becomes smaller as distance increases. It represents the pure attenuation of the line. The second exponential factor has a unit magnitude and contributes only for phase. So, for lossless line, R is equal to 0, G is equal to G. Hence, a lossless line does not attenuate. Since the attenuation is the same at all frequencies, a lossless line has no bandwidth limit. In addition, the propagation constant has an imaginary part that is exactly proportional to frequency. Since the delay of a system is simply the derivative of the phase with frequency, the delay of a lossless line is a constant independent frequency. That is, if EI and II are the incident voltage and current, then it's clear that Z0 is equal to EI by II. At the load end of things, the mismatch in impedances gives rise to a reflected voltage and current. We still have a linear system. Okay, we still have a linear system, so that total voltage at any point on the system is the superposition of the incident and reflected voltages. Incident and reflected voltages. So what is reflection coefficient? So what is reflection coefficient? What is reflection coefficient? So what is reflection coefficient? The reflection coefficient can be defined as the ratio of reflection of the wave that gets reflected back to the wave that incident. That is reflection coefficient gamma is equal to wave reflected by wave incident. The ratio of reflected to incident quantities at the load end of the line is called gamma L. Gamma L is equal to ZL minus Z0 by ZL plus Z0. The ratio of reflected to incident quantities at the source end of the line is called as gamma S is equal to Zs minus Z0 by Zs plus Z0. And also here the one of the important point is there VSWR, voltage standing wave ratio. It is also defined as the ratio of the square root of ZL by Z0. That is, here ZL by Z0 is say phi is equal, gamma is equal to VSWR minus 1 by VSWR plus 1, and gamma is equal to here gamma is equal to VSWR is equal to gamma plus 1 by gamma minus 1. Gamma plus 1 by gamma minus 1. So we will go for the wave equation in the next video. We will derive the wave equations.